In this tape, I want to talk about the philosophy of scientific investigation and how statistical design fits into that philosophy. There are so many things to think of in an experiment that you might be tempted to think that what you need is a huge all-encompassing experiment at the beginning which uses up your whole budget and you just think of everything to begin with. Well, that really doesn't work very well. Somebody once said, I think it was Fisher, that the best time to design an experiment is after you've done it. And that's a paradox. What he meant was that you think of a number of things. You say, well, if I knew what I knew now after I've done these experiments, I would have included this factor, I wouldn't have worried about that, I would have worked over here and not over here, and so on. So there's many things that you have to learn about as you go. And so the key points that I want to make in this tape is that investigations have to progress iteratively, that's step by step. The investigator is like a detective. You must use an adaptive strategy, and Conrad has talked a little bit about that, about sequential assembly. And because things don't all happen at the same time, you have to be sure to introduce blocking and randomization. And another point is that the investigator's objective can change. Another thing we're going to talk about is that graphical methods can spark insight. Graphical procedures are really better than just numerical procedures. So let's talk about the iterative nature of investigation. I want you to imagine an experiment on investigation itself. Let's suppose we've got 10. Normally you just have one investigator or one team of investigators looking at a problem. But to sort of get insight into what we're really talking about, let's imagine for this particular problem we've got 10 sets of investigators in 10 separate rooms, and we go into the first room, we tell them what the problem is. This is a problem in lubrication of an engine or something like that, and they're all, let's say, competent engineers in this field. We tell them what the problem is, and we just imagine the kind of things that they'll be discussing in deciding on some experiments that they want to run to investigate the problem. Well, I think one question they'll be thinking about is which factors should be studied. Now, it would be a miracle if they all came up with the same factors. When one of these examples we talked about before, we were looking at a molding problem, and there was mold temperature, moisture content, holding pressure, cycle time, booster pressure, cavity thickness, and there would be a whole lot of others. And the possibility that each one of those, in each one of those rooms, they'd all decide on the same set of factors that they wanted to look at would be very, very remote. There'll be a great deal of overlap because they're all experienced in this, but one guy will want to look at this and somebody else will want to look at that and so on. So you can see that the question about, well, what the mathematicians would say is what is the experimental space, that's really somewhat arbitrary. It's not the same for each group of people. Another question is, how should the response be measured? Now, you might think, for example, if you're doing experiments with computer chips, one of the problems about computer chips is getting a decent yield. So you might think, first of all, well, what we want to do is to increase the yield. That's pretty obvious. But suppose somebody came along and found a way of increasing the yield that cost, say, some enormous amount of money. So that, yeah, sure, you could move the yield up from 20% to 60%, but it would cost so much to do it that it just wouldn't be worth it. So you can see that there, it's not really yield you're wanting to look at, but cost per component. So again, there's somewhat an arbitrariness about those things. And when you start to think about an experiment, say you're looking at, say, temperature. I mean, are you going to, we've talked about, you're going to have a factorial experiment and then you're going to run at 140 and 160. Well, I guess one set of experimenters would think that was a reasonable range. Somebody else would say, let's make it 140 and 200. Somebody else would say, well, that's much too high. Let's make it 120 and 150 and so on. So some people will want a wide range, some a narrower range and so on. It's a matter of opinion, and it isn't going to be the same for each set of experimenters. And things like how complex a model You know, should we be expecting to have a lot of interactions and things like that? And that will be closely allied with what experimental arrangement, what experimental design are we going to use. So there'll be so many different things going on in those rooms. You can see that not everybody would be running the same kind of experiment. So trying to think of everything at the very beginning is not a very good idea, because you just can't think of everything in the beginning. It's the truth of the matter. So the way investigations normally proceed is an iterative one. Somebody has an idea, and in the light of that idea, they will get some data, and that will illuminate that idea. And so you now have the idea, you have the data, you put these things together and draw some conclusions. Now sometimes what you get it's pretty reasonable, it's the kind of thing you're pretty comfortable with and so on. But sometimes your initial idea and what the data says are really totally at variance. The original idea was wrong or has to be considerably modified. So by a process of induction, by a process of saying, well, what possibly could have resulted in what we're seeing here, you get a changed idea. This idea in turn, by a process of deduction, leads to saying, let's do a certain kind of experiment, let's get a certain kind of data and put that together. Again, it may or may not agree with what you expect. And so it's by this sort of process that an investigation moves along. It's rather like a detective novel. We've all read detective novels. Sherlock Holmes, Sam Spade, whoever it is. There's a body in the library with a knife in its back. The door's locked on the inside. Nobody can find the key, etc., etc. And the detective has to decide what to do. That's like an experiment, isn't it? He has to decide, shall I go and look for this one-eyed ticket collector at Baker Street Station, or shall I look for the telltale footprint under Lady Cynthia's window? Well, he has to decide, doesn't he? And he does decide, and he does something. He goes and looks under Lady Cynthia's window, perhaps, and there isn't a telltale footprint there. Well, there should have been, according to his theory. So he's now thinking, well, why isn't there? Okay. So what you're really looking for, you see, is some kind of investigatory process which is not unique, but which is something which will converge onto the right answer. And different people will go different ways. I think a very good example of this is the game of 20 questions. Let's suppose these people in these rooms are getting a bit tired of worrying about this problem. So you go in and say, okay, chaps, we're going to play 20 questions for a little while. And the object, let's suppose actually the object is Abraham Lincoln's hat. So we give them the clue. The object is animal and vegetable with animal associations. So the first team, Team A, what are they saying? Well, they ask a question, are the animal associations human? Answer, yes. Male or female? Male. Famous or not? Famous. Connected with the arts? No. Connected with politics? Yes. United States or other? United States. This century or not? Not this century. 19th or 18th century? 19th. Connected with the Civil War? Yes. Lincoln? Yes. Is it Abraham Lincoln's hat? Yes. Okay, so that's what's happening in one room. What's happening in another room? Same clue. They say, is the object useful? Yes. Is it an item of dress? Yes. Male or female? Male. Worn above or below the belt? Above. Worn on the head or not? On the head. Is it a famous hat? Yes. Is it Winston Churchill's hat? No. Is it Abraham Lincoln's hat? Yes. So they both arrived at the same conclusion, but they both went by quite a different route. So you're not looking for uniqueness, but you are looking for something which is going to converge. You can see a process here where you start from some initial point, you have some ideas, you perhaps run experiments which will test out which way to go. Sometimes you'll have to backtrack because something you thought was true doesn't turn out to be true, and eventually, by some reasonable logical process, you can end up with the answer. And this is not a unique route. What is needed, as I said, is a strategy which will converge. Now let's look at 20 questions again. In 20 questions you need two things to play it well. First of all, you need subject matter knowledge. If you never heard of Abraham Lincoln, then you aren't going to be able to solve that problem, are you? But you see, subject matter knowledge is not enough. There's a strategy aspect to this. When I play 20 questions, there's usually someone on my team who says something like, I mean, suppose we've got it down to the fact that it's stone. Okay, somebody said, is it metal or stone? It's stone. Well, when you think of stone, you think of these huge objects like big stone buildings and the Sphinx and all that, and you think of little things that are made of stone. And what unfortunately happens when I'm playing this is somebody on my side says at this point, is it the stone in my ring? And after you've said, no, it's not the stone in your ring, whereas before it could have been one of 10,000 things, it's now one of 9,999. That's not a very good strategy. It's going to take a long time, right? But there is actually a rule, a statistical rule, for playing this game, which is that at any given point, you should divide up the things that it still might be, ask a question which divides up the things that it still might be into two approximately equal groups. When they said, is it worn above or below the belt, for example, that was a good question because it does that. Male or female is a good question because it does that. Think of what it might mean to look up to try to find a word in a dictionary with 20 questions. You realize what you could find one word in a million words with this strategy. So you'd say, is it in the first half of the dictionary or is it in the second half of the dictionary? It's in the first half of the dictionary. Is it in the first half of the dictionary or the second half of the first half of the dictionary? It's in the first half of the first half of the dictionary, and so on. And actually, if you think of it, 2 to the power 20 is over a million. So you could find one word in a million by that strategy. So, see, an engineer or scientist must have subject matter knowledge. He must know his subject and so on. But he can greatly leverage his subject matter knowledge with statistical methods in the same way that you can greatly leverage your knowledge about everything when you're playing 20 questions by using a good strategy.